Okay, now let's turn our attention to the Flynn taxonomy. It's named after Michael Flynn, who was a professor at Stanford, and he came up with this hierarchy, I think, back in 1967, when people were just beginning to think about parallel computers. Incidentally, if you know Dr. Greg Bird in ECE, Dr. Flynn was Dr. Bird's PhD advisor. So the first kind of architecture that we want to talk about here is the SISD machine. Now, the Flynn taxonomy divides computers into single or multiple instruction streams, the number of instructions that are being executed at the same time, in single or multiple data streams. The simplest kind is a SISD machine, single instruction, single data, only one instruction fetch stream. But these really don't exist anymore. I mean, they probably do in embedded processors, a very few low-end and embedded processors. But as far as any computer you'd be using today, even laptops have multi-cores. So you just never encounter a SISD machine unless you're working in the embedded sphere. SIMD machines are different. They have single instruction streams, but the instruction streams work on multiple data items at the same time. For example, vector processors that work on all elements of a vector at the same time are SIMD machines. About 20 years ago, there were SIMD extensions to other architectures like MMX, I think was Intel's. And nowadays, GPUs just proliferate across the landscape. In their SIMD machines too, they have single instructions that work on lots of data streams. So if you had in a SISD machine, for example, if you had a loop like this, going from I equals 0 to A or to 7 and adding A sub I or adding B sub I and C sub I to get A sub I, in a SIMD machine, you just have A equals B plus C and do a vector addition instruction. It would add all of the data items at the same time. You can see that the different data streams come into the different ALUs. You have a single control unit here, and it sends out an instruction stream, and then you have a single data stream, or you have multiple data streams that are being operated on by the single instruction stream. So if one of them's doing an add, they're all doing an add. Okay, so the next kind is a Misti machine, which stands for multiple instruction single data. And there really aren't any Misti machines as Flynn envisioned it, but there's something that's close, and that's a systolic array computer. You can think of it as a Misti machine because the data stream pulses from one processing element to the next. So you might have one processing element doing an add and the next one doing a multiply. Right after one element adds two numbers, another element can multiply them. The two numbers that are being added, or more likely, a different set of two numbers. If it multiplies the same set of numbers that were added, then those numbers are being multiplied while another set of numbers from the same vector are being added. So you just have the data items pulsing from one stage to another. This isn't exactly what Flynn had in mind, but some people count these as Misti computers because otherwise Misti machines don't exist. Well, moving on to Memdi machines, multiple instruction, multiple data, you have multiple independent processors that are somehow connected together to form a multiprocessor system. You can have sharing occurring on different levels, anywhere from the cache down to the main memory, or maybe not even memory. Maybe you have separate memories and they have to communicate by message processing. You have different programming abstractions in use, specifically shared memory, which you can do if you have a chip multiprocessor because the memory's on chip, so of course it's going to be shared. You also have bus-based multiprocessors that we'll be talking about for several classes later on, where you have all the processors connected by a bus, so any memory operation that occurs needs to go across the bus. It's a very convenient way to synchronize memory operations. You might also have in a larger computer, you might have point-to-point interconnections. And in that case, you probably have something like distributed shared memory. You've got a network between the processors and the non-local memories. And then at the other end of the spectrum, you have clusters, most commonly, or grids, where the memory is totally distributed. The node that's close to me may have a certain amount of memory, then the node that's close to you have another set of memory. And if I want to refer to your memory, I've essentially got to pass a message over the network to get to it. Now that may actually be treated from the architectural level like a memory reference, but behind the scenes in the interconnection, it's like a message was being sent, and so it's correspondingly slower. So to start off with, you can have a shared cache architecture where you've got the tightest level of connection between the various processors. They communicate via shared cache, so you don't want to have too many processors in the same cache because you've got to multi-port it and it becomes very expensive. But really, more commonly, what you'd have is a private first level cache and a shared second level cache, so different processors can share the same second level cache. And of course, memory is beneath that. And then you have what are called UMA, or Uniform Memory Access architectures, where the networks are I'm sorry, not the network, but there's a network in between the caches and the memory, and that network is very often a shared bus. It may be some other kind of tightly coupled interconnection network, but in any case, you've got a network there, and in order to get from processor to memory, you need to go across the network, which, as I say, may just be a bus. So this implies shared memory hardware because you can make a reference from a processor up here, from any processor, down to the memory. Then we can have NUMA architectures. So UMA stands for Uniform Memory Access, which means that a memory reference takes the same amount of time, regardless of where in the memory it goes. With a NUMA architecture, you have your local memory and your non-local memory. So if a processor is referring to local memory, that may well be, in fact, that will be faster than if the processor is referring to non-local memory, in which case it has to go across the network, come back to the other memory. The interconnection network, some of the same interconnection networks are used for UMA and NUMA architectures. It really just depends on which side of the network the memory modules are located on. And then finally, we have essentially, like a cluster-based architecture, where you have the memory and processors on one side, and then you've got I/O units that interface with the network. And so it takes a longer time to get across the network here. But it's still possible to get across it, and depending upon the programming abstraction you're using, it may even look to you like you're using shared memory, but behind the scenes there are actually messages that are being sent across the network.